Welcome back to Mr. Vaughn's classroom. Before we get started, I ask that you hit the subscribe button, give this video a thumbs up, and drop a comment below if at any point you need help with what we're talking about. Today we're in Unit 6, Introduction to Quadratic Functions, Lesson 2, How Does It Change? The learning goal today is to describe some patterns of change. Specifically, we're going to look at linear, we're going to look at exponential, and we're going to look at quadratic. There's 3 learning targets today. Keep these in the back of your mind as we work through the practice problems. We'll come back to them at the end of the lesson, and we'll ensure that you've learned everything you need to from this lesson. Learning target number 1 says I can describe how a pattern is growing. So again, are we going to be adding the same amount? Are we going to be multiplying by the same amount? Is this going to be a linear pattern, an exponential pattern, or a quadratic pattern? Learning target number 2 says you can tell whether a pattern is growing linearly, exponentially, or quadratically. So we see that these learning targets really blur together. And learning target number 3 says you know an expression with a squared term is called a quadratic. And that's going to be the key in this unit, is understanding that if you have an expression where the highest power is 2, then that is going to be a quadratic expression. We have one glossary term today, and that is quadratic expression. A quadratic expression in x is one that is equivalent to an expression of the form ax squared plus bx plus c, where a, b, and c are constants, and a does not equal 0. And that's the important part here. We must have an x squared term, and it must be the highest power. So if a were 0, then anything times 0 goes away. We would no longer have this x squared term, and it would no longer be a quadratic expression. So it's very important we understand what this quadratic expression is. How many squares are in step 10? So the first thing we need to start getting used to in these lessons is going to be pattern recognition. And there's 2 things that I would encourage you to look for when you're trying to notice these patterns. The first thing I would encourage you to look for are squares. How can I arrange things into squares? In addition to looking for squares, look for squares that relate to the step numbers. So with that in mind, in step number 1, if you consider this one square, then you have a 1 by 1 square and then you add 1 square. Now we are in step 2. So if you will look at this square that I'm coloring in, you have a 2 by 2 square, and you add 2 squares. And then notice we're in step 3. So if I look at this square, I have a 3 by 3 square, and I add by 3 squares. So the pattern that we see is square with side length equal to the step number, and we add the step number of squares. So if I want step 10, then I'm going to have a 10 by 10 square, and then I am going to add 10 squares. Order of operations says we do the multiplication first. So 10 times 10 is 100. And when we add those 10 additional squares to the big 10 by 10 square, then we end up with 110 small squares. And that means our answer is choice D. If you have any questions about how to start recognizing these patterns, please leave a comment below, and I'll get back to you with any help I can offer. Here are 2 patterns of dots, pattern A and pattern B. How many dots will there be in step 4 of each pattern? So again, look for ways to relate the step number. And what I notice on pattern A is on step 0, I have 0 dots. In step 1, I have 1 row of 4 dots. In step 2, I have 2 rows of 4 dots. And in step 3, I have 3 rows of 4 dots. So if I'm looking at step 4, I expect there to be 4 rows of 4 dots each and that equals 16 dots. Now, pattern B, same thing. Let's look for ways to connect the step number. And I notice all of them have these initial 2 dots at the bottom. Then I notice that in step 3, I have what appears to be a square of 3 dots by 3 dots. And in step 2, I appear to have a square of 2 dots by 2 dots. In step 1, I could think of this as a square 1 dot by 1 dot, and then here I don't have a square at all, 0 by 0. So what I'm noticing is that the pattern for B is 2 dots plus a square that is step number dots by step number dots. So if I'm looking at step 4, then I expect to have a square that is 4 dots by 4 dots, and then I expect to have these initial 2 dots down at the bottom. So this gives me a total of 18 dots. Number 2, which pattern shows a quadratic relationship between the step number and the number of dots? Explain how you know. Well, a quadratic relationship is going to have an x squared. And the one that I see having a relationship to squares is pattern B. This has a formula or an expression that is the 2 original dots plus the step number squared. Pattern A is adding 4 dots every time, so it would actually be a linear relationship. So as we're looking for these patterns, these are the things we need to start looking for. Look to see if we're adding the same amount every time. If we are, that's linear. Look to see if we're multiplying by the same number every time. If we are, then that's exponential. And now the new one is look to see if there is some relationship to an input being squared, because that would give us a quadratic relationship. If you have any questions about any part of this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Here are descriptions for how 2 dot patterns are growing. Pattern A, step 2 has 10 dots, It grows by 3 dots at each additional step. Pattern B, the total number of dots can be expressed by 2 times n squared plus 1, where n is the step number. For each pattern, draw a diagram of step 0 to step 3. So we'll start with pattern A. We know that we're going to have step 0, step 1, step 2, and step 3. We know that on step 2, we're going to have 10 dots. So we can go ahead and draw that. Now, we know that it grows by 3 dots each additional step. So if step 2 had 10 dots, that means step 3 should have 13. Now, if we're adding 3 steps or 3 dots moving to the right each step, then we would subtract 3 dots going to the step to the left. So if step 2 had 10 dots, then step 1 is going to have 7 dots. And again, if we're moving to the left to a previous step, it should have 3 less dots, so now we're down to 4 dots. So that gives us pattern A. Now, for pattern B, they give us an expression, 2 times n squared plus 1. So for step 0, this would be 0 squared, which is 0. 0 times 2 is 0. And 0 plus 1 is 1. So step 0 is going to have 1 dot. On step 1, we have 1 squared, which is 1, times 2, which is 2, plus 1, which is 3. So step 1 is going to have 3 dots. For step 2, we have 2 squared, which is 4, times 2, which is 8, and 8 plus 1 is 9. So step 2 is going to have 9 points. And finally, step 3, 3 squared is 9, times 2 is 18, plus 1 is 19. So step 3 is going to have 19 dots. So this is how we can draw the diagrams when they give us the patterns. If you have any questions about this practice problem, please drop a comment below and I'll get back to you with any assistance that I can offer. Each expression represents the total number of dots in a pattern where n represents the step number. Select all the expressions that represent a quadratic relationship between the step number and the total number of dots. If you get stuck, consider sketching the first few steps of each pattern as described by the expression. So, a few reminders here. Linear is when you're adding same amount. Exponential is when x is your exponent. And quadratic is when you have x squared as your highest power. So let's look at choice A. We have n squared, so this is going to match having the input squared as our highest power. So A is going to be quadratic. And that's what we're looking for. B, we're taking 2 and multiplying it by n. So every time n increases by 1, our total is going to increase by 2. It'll go from 0 to 2 to 4 to 6 and so on. So if we're adding 2 every time, this is going to be linear. So B is incorrect. C, if you multiply n times n, this is the same as n squared. And that is what we had on A. So C is also quadratic. So C is a correct answer. D has n plus n. So if we tried to do this, what we actually have is 2 times n. We have n twice. And this actually matches what we had on B, so that means this is linear, so D is wrong. Now, if we look at E, we have n plus 2. So every time we increase our step by 1, then our overall total will increase by 1. We'd have 0 plus 2, 1 plus 2, 2 plus 2. So because we are adding the same amount every time, this would be another linear. So E is wrong. And the final one is F. We have n divided by 2. So what's going to happen is every time I increase n by 1, that 1 increase is going to be divided by 2. So I'm actually going to be increasing by 1/2 every time. We're going to start out at 0, 1/2, 1, 1 and 1/2, 2. So because we're adding 1/2 every time, that makes it linear. So F is incorrect. If you have any questions about this practice problem or any of the practice problems at all from this lesson, please leave a comment below and I'll get back to you with any help I can offer. Now, before we finish this lesson, let's go back, take a look at the learning targets, and ensure you've learned everything you needed to from this lesson. We had 3 learning targets on this lesson. Number 1 says you can describe how a pattern is growing. When you're thinking about this, think about things like, am I adding or subtracting the same amount every time? Am I multiplying by the same number each time to get the next number? Or am I creating a pattern where I'm adding some kind of square every time? Learning target number 2 says you can tell whether a pattern is growing linearly, exponentially, or quadratically. This goes back to that first learning target. This means you understand that if you're adding the same amount every time, then that is going to be linear growth. You understand that if you're multiplying by the same number each time, then that is creating exponential growth. And you understand that if you're adding some type of squaring of a number each time, then that is going to give you quadratic growth. And then the third learning target says that you know an expression with a squared term is called quadratic. And that is the most important thing to understand. That if your expression has something squared or something to the power of 2, and that is the largest exponent that you have, then that is a quadratic expression. If you have any questions about anything we've talked about in this lesson, please leave a comment below and I'll get back to you with any assistance I can offer. If you found this video helpful, somewhere on the screen down at the bottom, you should see a video that YouTube believes could help you out. You can go watch that one. You'll see the subscribe button. Please give this channel a subscribe. Give this video a thumbs up. And I look forward to seeing you again in the next lesson.